Hey everybody, this is Larry. This is December 19th of the December Leetcode Daily Challenge. Wow, what a month. Hope you're doing alright. Hit the like button, hit the subscribe button, join me in Discord. I do try to solve and explain these problems live or thinking about how to explain them. So feel free to go fast forward or whatever, because as I go through my thought process and not just the solution. Okay, so today's problem is cherry pickup 2. Which one is... Actually... I remember this problem because I was really annoyed about it during the contest. I'll put a link to how I about this problem during the contest. But this is just very straightforward application of dynamic programming. The reason why I actually got this wrong was I actually don't remember. I remember this picture or one of the examples kind of was really bad. And it confused me in that robot in this example, and this is kind of silly, but in this example what I did during the contest was that I thought that robot 1 and robot 2 can start at the corner, not just at the corner, but at 0 1 and 0 n minus 1 or n minus 2, because if you look at this example 2 picture, I thought that the robot could do the corner and also the square next to the corner, and because of that I got a wrong answer because that's not intended. But anyway, so I think other than that I actually got this problem immediately because I don't know, just a lot of practice on dynamic programming, and it's not meant to be a brag, but it is a pattern that comes up a bit in dynamic programming, and I think I just practice a lot. I would also say that, just to be clear, I probably at this point solve multiple hundreds of dynamic programming problems, maybe even 1,000. Because I don't really count per whatever. So yeah. So, and even then, it's still a little bit tricky for me sometimes. So I wouldn't think that badly about it. So the key observation about this problem that I made during the contest, and I remember this because I was really annoyed about this diagram, is why I remember this specifically, because if you watch me solve some of these, I don't always remember the problem or the solution, I guess. But anyway, so the key part to notice is that, well, I think in this case, let me just make sure, let me reread this just to make sure, because I haven't read this in a while. But so the key thing to notice is that every time step for each robot, you have to go down one, right? So that's observation 1. So there's no like staying back. And then the second observation is that it always makes sense to move those. Let's say you have 2 robots, right? I actually never thought about it this way, but just for sake of argument, if you try to move them one at a time, it doesn't really, then they're just more bookkeeping and tracking. But if you move them together, well, then the edge cases, and you could still do them separately if you're really slick about your dynamic programming. Maybe it should be okay if you're really careful. But for me, the more obvious way is to just move them both one at a time. And then now the edge cases are a little bit easier to handle, right? Because, well, if they're both in the same place, then, that's actually one of the tricky case, which is that the only thing that you have to handle is that if both the robots are in the same cell, you only get the cherries once. So that's the only case you have to handle. If that wasn't the criteria, if both of them can pick the cherries up, then they're actually just independent, right? Then you could do one and then do the other, and it doesn't really matter. But you have to take care of the special case where if they're both at the same cell. And the only time that they could both at the same cell is if they move down the same number of times. So in that sense, that was my logic, and from that observation, I just moved them both at the same time, because then now, if they're at the same cell at the same time, then that means that only one of them can take it, and you just do the math. Like, as an if statement, it's a math, it's a cost function, it's dynamic programming, and that's how I would solve it. And I would say I know that I'm a little bit hand wavy on the dynamic programming portion. I'm just going over my thought process, and we'll go over the code in a second. But I also want to say that this is, even though I may have made it sound easy, this is not an a beginner's dynamic programming. There are a couple of problems that are related to this for sure, and if you solve those first, it would make your life a lot easier, and also just like the progression, right? This is a little bit harder than the regular one. I think cherry pickup one is actually harder than this one, to be honest, but and it's not quite the same. So, but I think like in a general, like if I'm thinking about the standard dynamic programming problem for this, it's just going from top to bottom in the min cost, and it's kind of like the shortest path as well if you want to kind of do it that way. But it's also dynamic programming, and that comes up in all over the place, like content-aware resizing, for example, is one where you take the min cost from the top to the bottom, or max cost, depending on whichever you prefer. Anyway, that's a lot of context, a lot of background. Let's kind of get into code, because in code, I like to go over dynamic programming in code, because in dynamic programming, there are a couple. After you made these observations, then there are two things you have to think about, right? One is the base case, and the other is the transitional states. And of course complexity, I guess. But in terms of like those two things, then and the code is, especially in Python, I feel like it's very self-explanatory for those things, and so we're going to do that. Okay, and as usual, we take a look at the thing. But to be honest, it's going to be if you're familiar with this dynamic programming, it's going to be linear in the number of cells, which is all times C, say, which is row times columns. So I don't really worry about it, because if the input is too big, then you still have to look at each cell once. So that's why I didn't really look at the criteria this time, though usually I would recommend it. Cool. Though I would also say that maybe that's not necessarily true. Because now there's an extra complexity. So, but it is a nice glance to see that it's 70. So now you know that you could be a little bit lenient with your complexity, but we'll see. Okay, so now let's get, what is it, max? We want to pick up the max cherry, right? So let's just call it max cherry. Naming is terrible. Feel free to upsolve that at home. Okay, so then now we want to have, as we said, well, now we have a time step, which is exactly related to the rows. So you could call it time, you could call it row, it doesn't really matter. I'm going to call it row. And then now it's just the location of the first robot and the second robot. So C1, C2, right? So we'll go over the complexity later, because I like to just also, sometimes I'm wrong when I'm like, after I'm implemented, I'm like, oh, actually, this is not what I want to do. So, so we'll go to complexity later. Base case. What is the base case? Well, let's see. I just want to make sure that there's no weirdness. But okay, so base case is if row is equal to, let's just call it rows, then return 0. And of course, we'll set up rows and columns. So rows is equal to the length of the grid. Columns is equal to the length of the grid sub 0. And I'm just looking at the constraints to make sure that this doesn't give me an error. In certain contests they do, but in this case it's not. So you have to be careful about that. Okay. Yeah. So that's our base case, because and we're gonna solve this recursively. Obviously, I'm gonna add the memorization later. Don't worry about it for now. And also it turns out to be n cubed, so, or r times c squared. So maybe I lied about that one, about r times c. Yeah, okay. And that's why you have to still implement it, and getting a little bit rusty. But okay. So yeah, so now we go for our cases. And this is just an implementation detail. As we said, now we have 4 options really, which is that C1 can go, actually, now we could go straight down, right? So 9 options, because C1 can go, left, down, I mean, not left, just like down, left, left, down left, can't type, just down, down, right. And so there are 3 possibilities for C1, and of course C2 also has the same 3 possibilities. So so we can do that, and we can just like do for loops. I think I'm just going to do for loops. So yeah. How do I want to do it? So yeah, so let's just say DC1, D being delta, that's my notation. I don't know if it's a good notation, but just this. And for DC2, and you know, there are micro optimizations here as well. And this is 1. I don't know why I did -1 twice. This is how I mess up it in contest, because even as I say it out loud, sometimes I just miswrite it. So now we check, you know, I also have a notation for next C1, next C2 is equal to C1 plus, you know, C2, read my code, not what I say apparently. And then now we just have to check to make sure that it is within bounds. So if 0 is less than the new space that we're going to, and is less than columns, and of course we have to check the same thing for the second one. And then this is just recursion then, right? It's just max cherry of row plus 1, the new C1 and the new C2. So that's kind of the recursion transitive state. That's the transitional states or the transitions. Basically, you're just, that's the thing I like about dynamic programming. If you are able to think about it the right way, like the correct way for dynamic program, is that in a way it's brute force, right? Because you're literally trying everything. In this case, it's just, okay, so you have these 2 robots. Let's try, you know, robot left go, robot 1 goes left, robot 1 goes right, you know, all that other stuff, right? So like you try all 9 possibilities. So out of all those possibilities, the best one will, you know, we just take the best one, right? So that is very obvious in that it is brute force and just take the best. So that makes it easier. So here we have a best thing, and we, you know, we return the best. We didn't set it yet, I know. But yeah, so what is the, you know, in dynamic programming now we have to take what I call a score sometimes, but it just means in this case it's just the number of cherries you picked, right? So how many cherries did we pick? Well, in this new square, it is just grid sub I think I defined my states a little bit weird, but it's okay. So here we take it from, you know, before we go, and you could do a scoring function in either way. One of them is when you enter the cell, sometimes when you leave the cell. You just have to make sure that your base case and everything kind of corresponds. So there are different ways to write it. This is not necessarily the best per se, but that's the way that I kind of wrote it with my base case. But yeah, so now as we leave the cell, I'm going to take the cherries with me. So cherry is going to be, you know, where the robot is. And then we do an if statement just to make sure that if C1 is equal to C2 or not equal to C2, then we can also add the cherry from the second robot. Because if they're in the same space, then you only count it once, right? So this is going to be that. And of course, you just take the take that, and that's pretty much it. Basically here we just take the max cherry that we could take either from here or the previous best. Just want to make sure there are no negative numbers or anything weird. Okay, no, 0 to 100, so that's fine. So yeah, so now we just have to return max cherry. We start from row 0. The first robot goes, you know, it's from 0 on the left, and C2 is just columns -1. And because the way that we did it this way, we have to add the cherries. But and actually, I was gonna say that if it's only one cell, then they may start in the same cell. So maybe that's an edge case. But columns is at least 2 cells, so we don't have to worry about that. So we just have to add grid of from 0 of 0 plus grid of 0 to cos -1. So this does look a little bit awkward, more than usual. This is why when I looked at my base case and stuff like that, I was like, okay, fine. And that's why I hesitate, and that's why I also said this part. I'm like, we're gonna do it when we leave the cell instead of yeah. Wait, is that true? Did I double count it then? Yeah, I guess this should be okay, actually. Maybe. Well, let's check where to find. I know that I didn't cache yet for the memorization. So yeah, index our range. How is this index our range? I mean, I know that we don't check for that, but did I miss a typo somewhere? But we do call this earlier, right? So That's a little bit odd. A little bit odd. Odd. Oh, because this is rows, but they both should be columns. I think I'm just too used to doing breadth first search and stuff like that, and in that case you want to write dx dy, and the new x and the new y should be within bounds. I got so used to writing columns and rows, but here it should be okay. Okay, because this is a non-square matrix, which is good, because if it was a square matrix, it would have been right by accident. This might take a little bit too long because it is dynamic program. Oh, actually it's only there's 6, but yeah, let's put in more test cases. And again, I know that I didn't do the dynamic programming portion yet, so, or like the memorization portion more specifically. The dynamic programming, you can actually do this relatively straightforward with enough practice, so I recommend practicing as well. And I'll put a link below on the video of me solving or like doing dynamic programming progression video. And this is actually relatively fast, 44 millisecond. We're not going to do a big case. Let's just assume that it's going to time out, because it should. So basically now we just have to add the caching layer, and this is what I what I do for dynamic programming, is because I think a lot of people just add LRU cache or put in a map or something, depending on your language, and it's important to check the complexity first. So let's do that. Rows. Well, how many rows or how many different type of inputs are there to row? Well, it is just rows, right? Because it could go from 0 to rows, and so therefore it's O of R, say, just for a little shorter. C1 obviously is also from 0 to columns, so it's going to be O of C, and C2 again 0 to columns, so it's going to be also of C. Here we do a constant amount of operations, you could say, because this is just 9. I mean, I know they're for loops, but they're just 9 possibilities. So that's O of 1. So since this is O of 1 for each work, yeah. So let's say it again, which is that, okay, number of total possible inputs is equal to O of R times C square, and the number of, work each input does is O of 1. So in total, this is just, this times this, which is also just total complexity is O of R times C squared. Okay. And then, I didn't do the actual dynamic programming part, so the space part doesn't make sense. But the space is going to also be the number of possible inputs, because for each possible input, we just store it in a something. And then we're going to do that. And for now, let's just say, I call it cache because it is kind of what it is. And we could just set it to some thing times, times C for C plus 1, just in, I think maybe, for in range sub C plus 1, for in range of C plus 1. It's very annoying to write multi-dimensional stuff in Python, as you can see. So I don't even know. Oh, I think I messed up somewhere, because the last one should be, well, yes. See, as I was saying. And then let's have another one that's just the same thing, but to keep the Boolean value. I know that you can combine them, but I like to write them explicitly for educational purposes. So there you go. Okay, and then here we just have to check, well, if this is calculated, if this is calculated, then we return the result immediately from cache. And this is pretty simple, right? I hope it is, because especially for interviews, you should be doing this instead of LU cache. But yeah, and then at the very end, we cache the best answer, and also, obviously to label it as calculated. Calculated, yeah, use true. Oops, true. Okay, 44 milliseconds. Let's take a quick look to see if it's faster. Hopefully it is. Ooh, one timeout. I forgot that I named them rows and columns. Because I am actually usually write R and C, but today I guess I just feel a little differently for whatever reason. So let's fix that. One code again. Ooh, one time error. Oh, I can't spell, that's all. Calculated? I don't know how to spell calculated. Calculated? Did I spell that incorrectly? Huh. Calculated? That's... whoops. Calculated. Yeah, okay. That's hard. I mean, it's slightly faster, but it's going to scale way better, obviously. I'm going to submit. I clicked on the submit, but... Oh, there we go. It's a little bit lagging, but that's okay. Judging, accepted, yay! It's always nice to feel accepted. But yeah, so the space complexity is also going to be R times C times C. Cool. So this is my code. Let me know if you have any questions, and I will see you hopefully tomorrow. Bye-bye.